Hi everybody, hope you're having a wonderful day. Today we're going to talk about Chapter 25, Nuclear Changes. So please flip in your packet to this page where it says 3 types of changes. So in general we have 3 types of changes. We have physical changes, chemical changes, and nuclear changes. So far in Chapter 2, when we were talking about matter, we talked about physical changes. So these are changes that do not alter the chemical makeup of your substance. So the compounds, if you have any compounds, remain the same. The atoms remain the same. The chemical formula for every substance remains the same. But the physical properties might change. So for example, let's say I have a phase change. So evaporation, for example. So let's say I have some water molecules and there are some water molecules. Remember, these should be connected. Remember that they look kind of like Mickey Mouse. So that's in the liquid phase. If you have evaporation happening, then what you end up with is these water molecules, still H2O, still an oxygen connected to 2 hydrogens, but then now they are really spread apart as a gas. So you have H2O liquid staying as H2O, but now it's a gas. So it has a little bit different properties. Like a liquid flows, for example, where a gas diffuses and so on. So the main idea here is that the compounds remain the same. Your chemical formula remain the same. Then we have chemical changes, and we're going to talk about chemical changes a lot throughout this year. Chemical changes alter the compounds or alter the formulas, but the atoms or the types of atoms, the elements that are involved, remain the same. So the atoms remain the same, but are rearranged into different compounds. For example, the decomposition of water into hydrogen and oxygen. So if I were to write a chemical form or an equation for it, H2O would turn into H2 and O2. Remember, hydrogen and oxygen are diatomic. And just for fun, to balance it, you got 2 and 2. So what that looks like is you have 2 water molecules. There are your 2 H2Os, and then they turn into an oxygen molecule and then 2 hydrogen molecules. So the oxygens and the hydrogens remain the same. The elements or the atoms remain the same. You started out with 4 hydrogens and 2 oxygens. You ended up with 4 hydrogens and 2 oxygens, but they are rearranged to form different compounds, and so your formulas are different. With nuclear changes, these are changes in the nucleus. So if you remember from yesterday's notes when we were talking about the subatomic particles, we have protons, electrons, and neutrons. So the protons are what determine what element it is. For example, if you have something that has 6 protons, it must be carbon. If you have something that has 7 protons, it must be nitrogen. So protons determine the type of element you have, the identity of the element. Electrons determine the reactivity. The neutrons kind of help determine whether a substance will be radioactive or not, whether it will undergo radioactive radiation or radioactive decay or nuclear decay. So in a nuclear change, you have changes in the nucleus, and that produces most of the time different atoms or different elements. Some nuclear reactions happen naturally, like in the sun, for example, where the deuterium or the heavy hydrogen fuses together to make helium in the sun. And some, are reactions that do not happen naturally that we can have, in a lab, in a nuclear reactor. So what happens is that the unstable isotopes, you learned about isotopes yesterday, will undergo nuclear decay. And as nuclear decay happens, radiation is emitted. Now, when we say nuclear decay, that doesn't mean it decays into nothing. You know, when we think of decay, it means like, usually we think of the substance just going away, but in reality it doesn't go away, it just turns into another substance. And usually this happens with some radiation being emitted, and so the tool that we use to measure the radiation is called a Geiger counter. You know, like it's the device in movies where, you know, it beeps when you get to nuclear radiation. So there are many types of nuclear radiation that is emitted when you have a nuclear reaction happening. We're only going to talk about 3, alpha, beta, and gamma decay. And I know that you've covered that in physical science, so hopefully that should be a review for all or most of you. So we're going to start with alpha particles. So for alpha particles, they're named after the Greek letter alpha, the first letter of the Greek alphabet. And basically what it is, it's a helium nucleus. So what's inside of a helium nucleus? A helium nucleus, its atomic number is 2, so that means it has 2 protons. And its mass number is 4, so 4 minus 2, that means there are also 2 neutrons as well. So an alpha particle, one alpha particle is made up of 2 protons and 2 neutrons, which makes up a helium nucleus. It's not a helium atom because it doesn't have the electrons in it, just the nucleus portion. The notation for an alpha particle, you could write it in different ways. So you could write it as just the Greek letter alpha. Please don't write A though, it has to be alpha. You could write alpha with the mass number and the atomic number. So that would be a 4 and a 2. Or you could also write helium because it is a helium nucleus. Or you could write helium with the atomic number and the mass number. So any of those are acceptable. The mass of an alpha particle, remember that a proton is about 2,000 times more massive than an electron. We talked about that in our nuclear or in our atomic history notes. And we said also that a neutron is about the same mass as a proton. So you have 2 protons and 2 neutrons. Each of them is about 2,000 times the mass of an electron. And so combined together, the mass of an alpha particle is about 8,000 times an electron. The charge of an alpha particle, let's think about this. So we have 2 protons. The charge of each proton is positive, so you have plus 2. Neutrons are neutral, so the total altogether would be plus 2. So that's the charge of an alpha particle. The penetration, we say, of an alpha particle is pretty low. Because it's such a heavy particle, you know, relatively speaking, of course, that makes its penetration low. So a lot of things can block alpha particles. You can probably block it just with your clothing. The next type of particle we're going to talk about is a beta particle. So the Greek letters go alpha, beta, gamma, so that's why they're named after them. So beta is basically a high-speed electron. And in reality, when you have a beta decay, a neutron changes into a proton. So let's think about this for a second. Remember that protons and neutrons are made of quarks. So an atom has protons, electrons, and neutrons, and these are made up of even smaller particles called quarks. And if you haven't done it yet, please read the Top Quark article. It's one of the articles that I had given you. So a neutron is made up of several quarks altogether. So let's say that a neutron is made of 3 quarks, just for an example. So these 3 quarks all together make up a neutron. One of them is positively charged, one of them is negatively charged, and one of them is neutral. And so all together, they make a neutral neutron. And so that's just one neutron having many quarks. What happens with a beta decay is that it's a high-speed electron that leaves your nucleus. And so this part right here is gone. It goes out. So you can call it a high-speed electron, or you can just think of it as a quark that has a negative charge. And so that leaves. And so what's left, of your neutron is only two particles, the one that's positively charged and then the one that's neutral. So that's a proton. And so what happens is that negatively charged particle leaves, is gone by itself, and then so what's left of it is a proton. So a neutron changes into a proton with a beta decay. And we'll look at an example of that in a minute. So let's go back to our notation here. So since it's a high-speed electron, you can put an E, and usually we put the atomic number and the mass number, and so an electron has no mass number, it's 0, and its atomic number is actually -1, because it's kind of like the opposite of a proton almost. Or you could write a beta, the Greek letter beta, or you can also write beta with your numbers, so 0 and -1. Since it's a high-speed electron, its mass is the mass of an electron. And since it is an electron, it's a high-speed electron, its charge is -1, because an electron has a -1 charge. And its penetration is medium compared to the alpha and the gamma, because it is not as massive as an alpha, but it is lighter than a gamma. Let's look at gamma next. So the Greek alphabet goes alpha, beta, gamma. So gamma is not actually a particle. It's not matter. It doesn't have mass and volume. It's just a type of energy. And so the notation for it is the Greek letter gamma. And sometimes you can write it that way, and so other times you can write it with its atomic and its mass number. These are zeros. I'm sorry, it's kind of hard to write with a stylus. They're both zeros. The atomic number and the mass number for just energy would be just 0. Its mass is also 0. It doesn't have any mass in it. Its charge is also 0, but its penetration is very high. It's pretty difficult to block a gamma particle because it's so small. It's basically just energy, so it's very, very hard to block it. So now let's look at some nuclear reactions happening. So we'll start with a carbon-13 isotope decaying and giving off a beta particle. So to solve this, the first thing you want to do is you want to write down the atomic and the mass numbers for each part that you see in your equation. So carbon, in this case, has a mass of 13. It doesn't give us what the atomic mass, the atomic number is, but that's pretty easy to figure out because the atomic number is the number of protons, and that's what identifies the element. So a carbon atom will always have 6 protons, or an atomic number of 6. So you can put a 6 down here. A beta, we said, has a mass number of 0, an atomic number of -1. And then we solve it. So the idea here, whether it's a chemical reaction or a nuclear reaction, both sides of the equation need to equal each other. So this side before the arrow needs to equal to the total of this side after the arrow. So whatever is here, when you add it to a beta particle, needs to equal to this. So what you do is you say, okay, for the mass number, let's start with the mass number, you'd say this side needs to equal to this side. So 0 plus what is equal to 13? The answer is 13. So put a 13 there. Then you go to the atomic number and you say what plus negative 1 is equal to 6, because this 6 before the arrow needs to equal to whatever is here total after the arrow. So what plus negative 1 would equal to 6? That would be 7. So you put a 7 for the atomic number. And then you figure out what element it is. How do we figure out the element? Based on the atomic number. If it has 7 for the atomic number, that means 7 protons, that makes it automatically nitrogen. So you can see that with nuclear reactions, you can actually change one atom into a totally different atom, one element into another element, carbon to nitrogen. You can't do that with a physical or a chemical change. Okay, let's look at number 2. So number 2, we have nitrogen 15 decaying to give off a gamma particle. So same as the one before it, we're going to assign the atomic and mass numbers. So nitrogen has an atomic number from the periodic table of 7, so we're going to write a 7 here. Gamma, we know based on our notes that we just did, is 0 and 0 because it's just radiation. So then you say, what plus 0 is equal to 15? Because remember, anything on this side needs to equal to everything on that side. So what plus 0 is 15? The answer is 15. Then you say what plus 6 is 7. I'm sorry, that's not a 6. What plus 0 is 7. And so the answer is 7. And so that would be nitrogen 15 again. So in this case, my atom didn't change. It just lost some energy. And that energy is in the form of radiation. Let's move on to the next one. So we have uranium-235 emitting an alpha particle. And so uranium has an atomic number of 92. So I'm going to write that down. Alpha has a mass number of 4 and an atomic number of 2. So like we've done before, you'd say, what plus 2 is equal to 92? And the answer is 90. There we go. Then you do the mass number. What plus 4 is equal to 235? And so the answer is 231. So then you look up what element it is. If you look at the periodic table, element 90 would be thorium, TH. So uranium-235 can undergo decay to emit an alpha particle and turn into thorium. Okay, let's do the next one. So uranium-238 this time. Again, giving off an alpha particle. So we already know uranium has an atomic number of 92. And alpha is a 4. So 4 there and 2. So you say, what number plus 2 is equal to 92? The answer is 90 again. And then for the mass number, what number plus 4 is equal to 238? The answer is 234. And then we look up the element, and atomic number of 90 would be thorium again. Now this arrow here is telling us that basically uranium-238 gives off an alpha particle, but then it keeps going and it gives off a beta particle. So whenever you have a multi-step problem like this, what you do is you look at the product of the first one. So after it gives off an alpha particle, it turns into thorium-234. So then this thorium-234 you put here, and that gives off a beta particle. So let's do that. So thorium-234 and 90 gives off a beta, which is 0 and -1. So then you say, what number plus -1 is equal to 90? And so the answer is 91. And then for the top, you say what number plus 0 is equal to 234? And the answer is 234. And so now you look at the periodic table to see what element is number 91, and that is protactinium, Pa. The next topic we'll discuss with nuclear chemistry is half-life. And so when these atoms change into something else, we measure typically their half-life. Half-life is the amount of time that it takes for half of the radioactive substance to decay. And again, by decaying, we don't mean that it just goes away. By decaying, that means it turns into something else. So for example, carbon-13 might change into nitrogen. So how long does it take for half of the amount of carbon to turn into nitrogen? So to simplify things, we're going to use example of M&Ms. So let's say for number 1 that red M&Ms have a half-life of 7 seconds. So if you have a bag of 8 red M&Ms, you want to eat half of the quantity every 7 seconds, and we want to know how many M&Ms would we end up with after 14 seconds. Now when you eat M&Ms, they don't just disappear. They look like they disappear, but of course they are in your body and they turn into other things when you digest it. So it's not that it goes away, it just turns into something else. So to do this problem, we'd say, okay, well, we start with 8 M&Ms, and after 7 seconds, that's the half-life, half of it turns into something else. So we'd be left with only 4 M&Ms. Half of 8 is 4. But the question is asking 14 seconds, after 14 seconds. So if you go for another 7 seconds, then half of this amount would turn into something else, and so we'd be left with 2 M&Ms. So after a total of 14 seconds, 7 plus 7 is 14 seconds, so 2 half-lives have passed, we would end up with 2 M&Ms, so the answer is 2. Let's look at number 2. Let's say that yellow M&Ms have a half-life of 6 seconds. So if you have a bag with 24 yellow M&Ms, you want to eat half the quantity every 6 seconds. How many M&Ms do you have after 18 seconds? So let's try it. We have 24 M&Ms this time. And the half-life, they tell us, is 6 seconds. So after 6 seconds, 1 half-life, you'd be left with half of 24, which is 12 M&Ms. Then you're going to go for another 6 seconds, so that's a total of 12 so far, 12 seconds. Half of the quantity of 12, so we'd be left with 6 M&Ms. And then you'd go again for another 6 seconds. You'd be left with half of 6, which is 3 M&Ms. So after 18 seconds, 6 plus 6 plus 6, so a total of 3 half-lives is 18 seconds. You'd be left with 3 M&Ms. So number 3 says, let's say that orange M&Ms have a half-life of 5 seconds. How long will it take to end up with 1 orange M&M if you start with 32? So this time we have 32 M&Ms. Its half-life is 5 seconds. So after 5 seconds, half of 32 would remain, so that's 16 M&Ms. Then after another 5 seconds, we'd have half of 16, which is 8 M&Ms. Another 5 seconds, we'd have half of 8, which is 4 M&Ms. Another 5 seconds, 2 M&Ms. And then another 5 seconds, be left with 1 M&M. So let's count that. So we got 5 plus 5 plus 5 plus 5 plus 5. 1, 2, 3, 4, 5 half-lives. 5 times 5 would be 25 seconds. So the answer is 25 seconds. Put 5 there. Okay, let's do the next one. Number 4. It says, if you start with 16 brown M&Ms, and after 30 seconds you end up with only 1. What is the half-life of a brown M&M? So this one's a little bit different, but we're going to do it the same way. We have 16 brown M&Ms. So after the first half-life, whatever it is, we don't know how long it is, we'd end up with 8 M&Ms. After another half-life, we'd end up with 4 M&Ms. After another half-life, we'd end up with 2 M&Ms. And then after another half-life, we'd end up with 1 M&M. So we don't know what the half-life is, but we know that it took a total of 30 seconds to go from 16 M&Ms to 1 M&M. So the arrows here represent our half-lives. And so we have 1, 2, 3, 4 half-lives passed by in order to go from 16 to 1. So you would say that we have 30 seconds divided by 4 half-lives. That's a symbol for half-life there. T with 1/2 as a subscript, but that's not a big deal. So then that means that your half-life is equal to 30 divided by 4, which is 7.5 seconds. Okay, let's try number 5. So now we don't have M&Ms, we have real substances there. So uranium-239 has a half-life of 23.5 minutes. It says if you start with 12 grams of uranium-239, how long will it take to have only 3 grams of uranium-239 left? So we do it the same way. So we start out with 12 grams of uranium. After the first half-life, which is 23.5 minutes, oh, it's kind of hard to read, we'd be left with half the quantity, which would be 6 grams. And then after another half-life, so another 23.5 minutes, we'd be left with 3 grams. So we've reached our goal of 3 grams. It took us 2 half-lives to do that, and so that's a total of 23.5 minutes times 2, which is 47 minutes. So the answer is 47 minutes. Let's try the last one. You have 400 nuclei of a radioactive isotope. After 1 hour, only 50 of the original nuclei remain. What is the half-life? So this one is similar to number 4 with the brown M&Ms. But we do it the same way. So you'd say we have 400 nuclei. After the first half-life, we're going to end up with 200 nuclei. Second half-life, we'd end up with 100 nuclei. And then after another half-life, we'd end up with 50 nuclei. We started with 400, we ended up with 50, and it took us 1, 2, 3 half-lives. They tell us that that took a total of an hour. So you would say, you can do it in hours. 1 hour divided by 3 half-lives. So that's 1/3 of an hour. Or you can say 60 minutes instead. divided by 3 half-lives, and so it'd be 20 minutes. So you can either say a third of an hour or 20 minutes. 20 minutes would probably be better. In chemistry, we don't usually use fractions. We typically use decimals if possible. That's it for today's lesson. You have time to work on your nuclear presentations if you would like for Friday. Have a great day.